All right, this is day 2, or still day 2 of 3.6, but the third example. So you will notice you have a just a little bit bigger of a polynomial within your rational function here. So your numerator is a higher degree cubic than your denominator. So you know for your end behavior asymptote, you're going to do some division. Before we get there, though, of course, you can factor the denominator to get those vertical asymptotes, right? So that factors down to x minus 4x plus 2. And before I state my vertical asymptotes, I'm going to factor the numerator as well. And that one's not so obvious to factor. And so you could use the rational root theorem, like factors of 6 over factors of 1, and synthetically test them to find the zeros. You could also take a peek at it on your graphing calculator. So if you notice in Y1, I just typed in the numerator. And I'm just going to graph it really quickly. And it appears that it's crossing at 1 and -2 and -3. So the factors then would be x minus 1, x plus 2, and x plus 3. And so I will set those up as well. Okay, so the tricky thing about this question is that it's definitely more complicated with the pieces you have to think through, but you also hopefully will catch that x plus 2 is redundant in the numerator and the denominator. And remember that that means there's a hole in the graph at x equals -2. So I'm going to make a note that there's a hole in the graph at x equals -2. And I'm going to come back to that. But personally, I would also highlight that common factor, like I circled it, so that I don't use that, because you can't be a hole and an asymptote. So that -2 is a part of nothing else, right? And so really, actually, I would probably just kind of slash through this at this point, but I do have to make note of the hole when I do my graph. So now if I FOIL out what's left in the numerator, x squared plus 2x minus 3, and my denominator, I just have an x minus 4, right? So I'm just going to kind of show like that's really what's left in terms of graphing. So now my vertical asymptote, if I set my denominator equal to 0, I'm just going to get x equals 4. And my numerator, of course, well, you can see still up here that my x-intercepts are going to be 1 and -3. So I still have to do long division here, or I'm sorry, I still have to do division, but thankfully not long division. Up here I would have had to do long division, right, because I'm dividing by a quadratic, but now I can do synthetic, and I will get the same end behavior slanted asymptote here as I would if I divided the original blue. So good news, right? It wouldn't matter if you didn't catch the hole, you'd still get the slanted asymptote correct. So if I do synthetic from here off to the side, so I'm dividing by 4, coefficients are 1, 2, -3. And remember, I don't care about the remainder with the slanted asymptotes. So this is just y equals x plus 6. So, here's 6 and then slope of 1. So I'll have a slanted asymptote somewhere over there. So if I unveil the graph, this is what you would see on your graphing calculator. I put the hole in at -2. That's really, really important that you show that on your graph. That shows you that you recognize there's a hole. And you can probably, hopefully, see the slanted asymptote as well. And that's at x plus 6. I can just kind of put that in there. So the x-intercept is 6 and the slope is 1. You can definitely tell. And the only vertical asymptote is at x equals 4. And again, you can see that as well on the graph. And you can see the x-intercepts at -3 and +1. And the y-intercept, I didn't talk about the y-intercept, but if you plug 0 in for all the x's here or here, it doesn't matter. But you'll get 3/4 for the y-intercept, and you can see that here as well. So really, again, if you go to your graphing calculator, and I will turn this one off and turn on the entire rational function here. And it doesn't matter. You don't have to worry about the hole when you're graphing it on your calculator. However, your calculator doesn't show the actual circle for the hole, but you'll see it on your table, and I will reference that in case you have forgotten after this slowly graphs. Well, anyway, I could adjust my window here, but I'm just going to go to my table and remind you, you can pick out some good points. Also notice that at -2, you see an error, and that is not an asymptote, that's the whole. So you would have to be able to catch that anyway. Plus, if you go back to the graph and look at -2, you don't see an asymptote, so hopefully then you would realize that's a whole. As you trace along there as well, if it actually traced to -2, it will just jump right over it. If it actually landed on -2, it'll give you an error message. So last example, just kind of a fun one, seeing if you can kind of work it backwards. So given all these pieces on a rational graph, could you actually write the rational function? So you know you have two vertical asymptotes, you have an end behavior asymptote at y equals 3, x-intercept at -1/3, and a y-intercept at 1/6. So probably strategically a good place to start is, okay, I know the vertical asymptotes are in my denominator. So turn these into factors, x plus 4, x minus 3. And I also know my x-intercepts are factors in the numerator. Okay, now the thing you need to be very careful about when you have fractional values, when you write them as factors, you want to make sure that you don't write them as fractions. So if I solved 3x plus 1, that would give me the x-intercept of -1/3. I'm sure you see that connection, but it's very critical that you write that, because then your leading coefficients would be correct. Okay, so I took care of verticals and I took care of the x-intercept. Now the end behavior asymptote of y equals 3, well, since it's y equals, it's just a horizontal, right? So I know my degrees need to be the same. Well, right now I have quadratic on the bottom and I have a linear on the top. So I know I'm going to need another factor, or at least another x, to make those degrees the same. And if you think about it, if well, actually, let me FOIL out the denominator. It's kind of optional, but if you FOIL out the denominator, that's all I did here. If I make this x, when you FOIL, this is going to be a 3x squared. And if you divide out now your leading coefficients of 3x squared over x squared, you will get 3, and that's supposed to be my end behavior asymptote. So I know that this is x. Okay, well then, if you continue to FOIL, I don't care about my outer and my inners, but my last term, this 1 times whatever, unknown, I know that my y-intercept has to reduce to 1/6. So whatever I add here, or I should say subtract, needs to be a 2, because I know -2 over -12 will reduce to 1/6. So if this is a +1, this needs to be a -2, so that when you FOIL, you get the -2. And then you don't actually have to FOIL that out, but if you wanted to finish, now my outer is going to be -6 plus my inner of 1, so that inner term would be -5x if you want to FOIL, but you don't have to. So really, you could just leave your expression like this. You don't have to FOIL the denominator either. It was just maybe necessary to see key pieces.